preocupa esta. Me preocupa la logística.
All right, you're live.
Okay.
Okay.
Maybe we could wait.
Yeah.
2 or 3 minutes. There's a few other people who mentioned they would come.
Sure.
Of course, there's no chairs left in case they do. Yeah, there's
And another one there. We can bring more.
You know, one thing that I haven't met you. Okay, so it's good of a thing for you to introduce yourself. Very many of these guys are already here.
Okay. I will work on my own business model.
Welcome.
Welcome.
Again, to have you here. So basically, you get the job that day, the week was going on well.
I don't have really the same background.
Good. You come from France?
Yeah. I did my PhD in South Africa.
Great. Great to have you here.
So you are being upscaled.
Regional model too. Good one. Good one. Your login message was on.
I hope that we pick Piranha.
No,
I don't
Nemo.
think so. I think it will be Nemo.
Yeah, Nemo.
I like Piranha.
Piranha was a Koopa, very close.
A Cooper was better.
Yeah, Koopa. And
The suggestions for the cluster name?
the new cluster.
It's supposed to be sharp deleted or something, right? That's usually what
Yeah, I suggested Salicant, but
I
nobody.
did.
No. Come on, I think it's just a Piranha.
cluster. All the clusters, I think, are named after
Okay,
sharks.
now, let me introduce Jorge. Great.
I'm going to go look for Jim.
Sure, yeah. We still have, yeah, we still have the open.
I think Ashley might come. I'll pull that.
Hi.
Steve. I think Ashley and Steve.
So, Jorge Corral works for the University of Uruguay, School of Engineering. And I think you'll find interesting. He has been doing some work in the agricultural sector, and as you know, we are starting a project with the World Bank in Uruguay, with the Ministry of Agriculture. And a lot of what Jorge has been doing is really relevant. And we will find our way to involve you as extensively as possible.
Sure.
So, great to have you here, Jorge.
Thank you so much. Well, good morning to everyone, and thank you very much for being here, and also for all of you for being so open and welcoming with me. I will do my best with the English I have, and I will do my best not to talk too much. I will try to keep taking 35 minutes more or less. Well, this is an actual scene from Uruguay. Just to talk a little bit about my background. My background is in computer science, so I am formerly a systems engineer that someday decided that he didn't want to be all day researching in very super abstract things that too few people would actually understand, and much less to see which could be the actual value to whom of those things. So when I started to know a couple of agronomists that are now my colleagues in the team and also my friends, I started to see, well, these guys are also researching, but they are like researching with actual real problems of real people in real life. And that kind of moved me. Okay. So I decided to do my master's in agroinformatics, which is basically applying IT-related concepts, methods, and tools to agronomic problems or ecological problems or agroecosystems in general. So that's more or less my introduction. I won't bother you with any more. To show a little bit of the team that we build, we are around 8 to 10 people that are working with this topic down there in Uruguay. A couple of them are agronomists. Many of them also hold masters or PhD. And well, I work, as Walter said, in the University of Uruguay in the School of Engineering. And we have the help of the French IRI, which is like a research institution but, in development and agronomical stuff, but not in the country itself, but out of borders of France. And actually, Pierre Baumel, I hope I pronounced that well, Pierre was one of the first guys that introduced us to all these multi-agent systems topics, and he works for the green team of the CIRAD, and he's now posted in Brazil. Actually, also working with the federal government in Amazonia-related research. Yeah, he was in Brasilia, and he was just transferred to Sao Paulo. And well, we also have very much ties with the Plan Agropecuario. That's an institution that is of the government, of course, that their main aim or objective is to work directly with livestock farmers. Okay, so several of these guys that work in the Plan Agropecuario, they are generally agronomists, but they are extensionists that they work directly with a lot of livestock farmers. That's also why a couple of our projects and probably our main expertise specific in the math topics are applied to livestock farms. But in general, we are interested, as you said, we are specializing in livestock farms, although we are interested in applying multi-agents to agroecosystems like in a general way. What we do, well, agent-based modeling, that I will discuss a little bit what they actually are, to develop prospective scenarios of agroecosystems. So we are very careful in not promising that our tools are oracles or crystal balls or whatever. I'm sure that you perfectly understand that, but when you talk to farmers or decision makers, they want to keep it like much simpler. They want it like black and white. They say, wow, press play and I want to see what will happen in 10 years. Oh, no, you know, you have to cope with uncertainty. That's how life is. Okay. So I will first start introducing the multi-agent system concept. From one side, we have an agroecosystem, which you will probably know this better than me, so I don't want to be embarrassed. And on the other hand, you have the multi-agent systems approach, like in general, or at its most pure form. You have agents, you have an environment over which you have resources in general. You have agents perceiving that environment and those resources and acting upon them also. They generally have some kind of sphere of influence. So although you can make an agent know the entire environment, that's usually not a good idea because it's not generally true. And the agents are able to communicate between themselves. So this is like kind of the general theory, super brief, of multi-agent systems. Multi-agent systems, at least in the context that we are studying it, came from artificial intelligence and distributed intelligence. Okay, and for example, maybe you have seen, or at least we do it in the School of Engineering, these kind of soccer robots that they play by themselves. Well, that's also an example of a multi-agent system. In that case, the actual robots are physical instantiations of agents. But the idea is that there is no centralized control. Each one of them has their own rules, and they can communicate, coordinate, negotiate, fight, or whatever, but each one has rules, and they interact some way between themselves and also with the environment. And something emerges, for example, they score, or in our cases, sustainability itself could be an emergent property of these kind of complex systems that we are modeling. Okay? Please interrupt whenever you want. So we are trying to take these two worlds together. So an agro-ecosystem representation using the multi-agent systems approach would be having producers as agents, having land plots, neighboring cells, the soil, the nutrients, etc. as the environment, the weather, the climate. Oh, I should have drawn a cloud here. It would be much friendly for my audience here now. Then resources over that environment, like cattle, crops, or whatever we are interested in modeling. Of course, the producers perceive how their farm or their cattle is, and they act upon accordingly, and they have decision rules or decision trees that would apply on each time step of the simulations that we do. And of course, each producer has very much knowledge of their own farm, but maybe they can also see the neighboring farm, for example. And of course, they are also, or they could also be in interaction with each other, and they could even form higher forms of organization, for example, an organization of farmers in certain counties. Okay? So this would be the more social subsystem of the agro-ecosystem, and this would be the biophysical subsystem. So I hope this more or less shows how we conceptualize, how we look and understand the agro-ecosystem in terms of these theories. Okay. The methodology that we use in our project is more or less like this. We are very much concerned in not being isolated in an office and only talking to ourselves. So we try always that the first phase of the project are very participatory, so we involve the actual stakeholders. And then I will show an example on the drought phenomena in the northern Uruguay. So we try to do plenary sessions, workshops, surveys, interviews, and that you should add the expert knowledge of the guys on the field. But we also have direct contact with the stakeholders. After that, we start doing some, well, maybe a lot of UML modeling. I will show then a couple of examples, but UML stands for Unified Modeling Language, and it's a graphical language that was started originally from the computer science field, but it's now much more widespread use. And instead of writing, you draw diagrams, basically, but those diagrams actually avoid all the ambiguity that natural language has. Okay? And well, I will show you later, but the UML has several types of diagrams, and each one allows you to model different aspects of certain reality, like more static aspects or dynamic aspects or whatever. Then we start to translate those models that they can be in paper, in a software tool, or in a whiteboard, and then we translated them to a multi-agent system simulation. This is actually a software that will run, so someone has to program it. Okay, and for this we use a lot the format simulation platform that is from our friends of the French CI. I will show a very short example. And that we make some sensitivity analysis. We see the general coherency and consistency of our model, and then again show it to the stakeholders to see what they think about it. So these two activities would be done and the other 2 on the field with the producers. Okay. Of course, sometimes we try to simplify some of the output or some of the diagrams in order to get them validated by the direct stakeholders. And a little bit of the modeling process that we use. Well, we start from this conceptualization of an agroecosystem using the math approach. Then we do all these Eagleman diagrams. Here we have like hello world examples of 3 of them. This is a sequence diagram, this is an activity diagram, and this is a class diagram. I will show them a couple of examples more interesting about this. And then we summarize all this, and we actually start to program on the Corma simulation platform. We could use any kind of programming language, but the simulation platform already has a lot of what we call APIs that it allows you like to automatically build this more or less nice output, and then it allows you to easily graph the results and put the input, etc. Well, this is the case study or the research project that I told you earlier. Most of the northern part of Uruguay has basalt soils, basaltic soils, which again you would probably know more than me, but I know they're like rocky soils, and they dry out very easily. Okay, so the drought in that region is like a real big problem for livestock producers. So the objective of this research project that was funded by the National Research Agricultural Institute of Uruguay, the objective was to contribute to the understanding and communication of the drought phenomena over basalt soils in North Uruguay in order to, like the big aim, to improve the livestock farmers' adaptation capacity over those droughts. And we started by describing and evaluating the different drought adaptation strategies. And there we find especially 2 adaptation strategies. We could have found more probably, but we also wanted to keep it simple, and we ended up with 2 rationales. One, it was a kind of proactive producer, and the other one was a kind of more reactive producer. But we also have to be very careful in not using those actual words with the stakeholders, because nobody wants to say, oh yes, I'm a reactive producer, so I will act late or something. And well, after understanding and capturing those 2 rationales, we validated them with the producers, and then we actually started all the modeling process. And of course, our main idea was to say, well, we have 2 strategies that we know it represents the majority of the stakeholders of the farmers that we know. But is there one strategy that is always better than the other, or in which context one would be better than the other? Because actually what we saw in the real world was that the 2 kinds of producers, the 2 of them would be cases where the 2 of them would strive, or other cases that the 2 of them would go bankrupt. So it was not easy to see one of those strategies was inherently better than the other. Then how does the herd evolve under these drought conditions? And actually this model had 3 versions. On the first version, we were only interested in modeling the grass growth. Okay? And we were using some grass growth rates that were taken from satellite imagery with the help of the University of Buenos Aires that does the processing of the satellite images. Then we used climatic data from a 10-year series, and then we just repeated it over and over again into the future. And of course, we know that's not a great idea, but and we would probably get a good help from you guys sometime. Since if you just repeat the climate as if like repeating it to the future, you generally get this kind of cycle that repeats in the simulation. Okay, so actually have good understanding and a good use of climatic information into the future would be a great deal for us in this kind of project. And well, there were actually dozens of producers directly involved, and it was funny, so to speak, because in many cases, well, we brought here also from France and Brazil, and we went to the field, and in many cases, the producers were have floods. And they would say, well, we are talking about drought and floods, but they said, well, that's great, because we don't want to talk about drought when we are in a drought. We have to do it before. Well, I already talked about the conceptual tools that we use, the UML and the system, and I will show you a little bit about the software tools that we use. We use Excel spreadsheets, the Orma platform that I was talking, and also lately we are using web-based video games. The idea behind this, that I will show some examples right now, the idea is that especially the core math simulation platform and the core math simulation model itself is quite complex. And even for us that we build it, it's not easy to change things, to do all the running of the models, to understand why something is happening. So it would be actually impossible for a farmer to directly use it. And even it will be impossible for the technical agronomists that assist the producers in their farm. So we started to see a more wider spectrum of choices of tools, okay, that they are targeted to different audiences. So for example, this is the mechanic model, which is actually an Excel spreadsheet. Maybe it looks nicer than most Excel spreadsheets, but it is no more than a spreadsheet. And this is like for our main audience for this is, as I said, the technicians that work directly with the farmers, since they are so very used to use Excel as their primary tool. And of course, you have like a limited capacity in these kind of Excel models. You cannot all do the things that you can do with the Orma simulation platform. Okay, but the good thing in the trade-off is that anyone can use this kind of Excel sheets, or at least the technician. But also one of the limits, of the restraints that it has is that in order for simulate some like 10 seasons, you have to actually complete all the data and go to the season, complete and go, complete and go, complete and go. And actually, all the decision making is made by the user of that spreadsheet. In our core math model, the decision making is embedded inside the model. So you just press play and cross your hands and see how it evolves. Okay, so they are actually different, very different tools, but with the same core formalized principles and methods.
So you're saying that the spreadsheet does not model decision making, but the software does?
In our case, in this project, yes. Yeah.
So the spreadsheet is mostly calculation of sort of the environmental response to
the decisions that you are making. Exactly. And it's just like useful for this system.
Yeah.
To change all the parameters of the next system. Or actually some of them will be calculated for the next system, and then you would take decisions over those. This is an example of a performance model. This is not actually the example of the drought. This is an example of the dynamics between soybean and cattle. It was another project that we did. The red dot means that the primary activity is cattle. The yellow one is soybean, and the green one is in between one activity and the other. But this is how the core math model looks like, and you can like tap in any of these, and it will tell you, well, this is the plot, blah blah blah, and it belongs to the farmer, blah blah blah, like right-click and see a graph that shows the plot and whatever you want to test over that. So this is the you need someone that truly knows how to program these kind of things and also understands how to use the context. Well, each time step was an year, okay? And what is shown here is in one scenario that I don't remember which one was, but we had a scenario, for example, where the soybean prices went up and the beef prices were stable, for example. And you started to see how the farmers react to those changes and started to rent their stocks to the investment fund managers that were one of the agents. And these guys, they only do soybeans, so they will actually pay more for the rent and put soybean in that plot. I have at the end two examples that show a little bit the rationale behind it.
What is the spatial resolution for the pixel? Does it represent real farm?
Well, in this case, if I remember well, each plot is like 100 hectares. But actually, we just wanted to represent an enough quantity of land plots to see like a more general landscape. But we are not using the actual geographic information. I mean, we don't care if the farmer is here or is here, or if a farmer has all his land. That was not an issue for us in this case. But you can actually say, well, I define something exactly this, and you can also even put a GIS over this to actually see on the actual ground how it looks. That's all thanks to Kotlin. And this is one of our latest projects that we got funding. This is really a game. It is a web-based game. And as I said, what we wanted to do here is like to wrap up in a nice and friendly view all the sound knowledge that we are building on all these research. So this is not like a easy game. I mean, it's a pretty serious game, but it's a game anyway. Okay. And I was just a couple of minutes before starting discussing this that what are we going to do with it? Well, we don't know yet. We wanted to explore and see how it would be to take some parts of the models and put them in a very natural way to use it. But should the producers directly use it? Well, maybe. What we are seeing now is that in high schools, they are very interested in using these tools, and probably in the first year of university courses in agronomy, they also are interested in using these kind of tools. Where this will end, I honestly don't know.
Can you explain how to use it, or what are the functionalities?
Well, more or less, you have like, well, you always have 9 plots. It's not dynamic yet. You have in each of these plots. How do you say one of these?
Plots.
You're right.
Fields. Okay. You have a certain amount of livestock in each one of them. Even though we always draw one, when you hover the mouse over it, it will give you more information. For example, this plot has 25 hectares. The average grass height is 4 centimeters, and we have 45 head count of livestock there. And the pregnant cows have an average weight of 380 kilos, and the actual
Stocking rate.
stocking rate is 1.8. And so you can see like a snapshot of now that is spring, yeah, spring in September, and you can buy livestock, you can sell, you can supplement, and then go to the next season and see the results of your decisions in that next season. It works kind of the Excel model, but in a much more friendly and easy way.
So you can do scenario analysis. You can do scenario analysis in the game platform.
Yes, the thing is that you have to like run it very like step by step. So if you want to like run a lot of steps under certain circumstances, Cormas would be much more easier to do that. If you mean that.
What does all the logic in it? What's the programming platform? Does it connect to Cormas or?
No. This has nothing to do with Cormas. This is over Unity, and it was developed on C#. Okay. Unity is like a gadget that you program in C# and then you throw it. It's like a new kind of Flash.
Let me just clarify. This is exactly what a farmer has to do every season. For example, he's getting into spring, and he knows that the grasses are going to grow around. He has many choices. He can buy more cattle, he can sell cattle and do something, rent it to soybean. There are many choices. This is a simple game that will allow you to see what is the impact of different decisions. So if he has a starting amount of money, he has some degrees of freedom for making decisions, and with given climate conditions, which is not variable, this is what you will expect. So the nice thing is that you are doing decisions at the pattern, at the plot level, but you're also seeing the result of the farm. It's nice. It's simulate the interactions between farmers or non-farmers, or
We didn't make it. We could.
And do you have the climate information there somewhere?
Well, here, yeah, it is, and you can look at it, but it's like, well, this season was like this. Like, it tells you how it was. And we put it against the same 10-year series, I think from 2000 to 2009, and then we repeat it over and over again.
Yeah.
have a simple outcome of a result of a scenario, for example.
No, I don't know.
Like an output.
What a parameter in the simulated process. Do you have a PowerPoint that to show?
No, I don't have it right now. No, we did those kind of run over the Cormas model, not over this one.
Would someone playing this game currently, they would be controlling all of the plots?
Yes, because this is like your farm.
Okay, and so you would be able to move animals between the plots?
Yes.
Is that game already available somewhere? I can play now when
you could. I can ask for that. Yeah.
But this is more like a prototype. It's something that you're working on,
Yeah, sure.
trying to figure out, for example,
Yeah,
what other variables you would like to include there. And
Yeah, I would say that this is like a kind of beta software or beta game based on all the research we've done in this specific drought phenomena project. We still have to test it further and see actually, as I said, well, who will be the target audience? For educational purposes, it might be great, but maybe it's not us that should uptake this model. Maybe it's our colleagues that actually teach these courses. Well, we have a postgraduate course about modular systems in agro context. We will probably use it in our own course to show it as an example. But we are not sure if it's the right tool to use with the farmers. So that kind of thing, we still have to figure it out. But I would say that it is pretty finished for what we expected, but we are not quite sure how to use it or with whom to use it. Okay.
when you start thinking about developing this game, I'm pretty sure that you thought about that what would be like your target audience.
Yes, well actually our original target audiences were the farmers themselves. But we are not sure that it will totally fit for a farmer. I'm not sure. Well, this is what we want. We are very open, but in any case, this is my first visit here, so I just want to like get to know each other, and hopefully someday we can do something together. And I will briefly show you. This is the static model. It's actually a class UML diagram. It shows like a static representation of the animated GIF that you were seeing. Okay, the cattle was the red plot, the soybean was the yellow plot, and the MT was the green one. And at the left here we have the agent part of the model. We have two different kinds of agents: the traditional family farmer and the investment fund manager. They are huge companies that they invest typically in soybeans, soybean crops in Argentina and Uruguay. But nevertheless, they are two kinds of producers. So actually, the semantics of this kind of line is like a kind of typology thing. And you can say, well, the producer is described by estimated profit, by consumption, by productivity. He can produce something. The investment fund manager has certain productivity, which is higher than the traditional one because he has more access to machinery and all that. And for example, the traditional farmer rents his plot to one of these investment fund managers, but actually the traditional one still holds the property of the land. That's how we model it, and that's more or less how it actually works. I mean, these huge investment fund managers, they don't go and buy the land; they just rent it, and that, of course, makes you suspicious about the things they use, like chemicals and all that. So we didn't put the soil degradation in this model, but we could. But then again, that reminds me that what I talked with yesterday with Manu, that it's so very easy to continue to add things. And everybody will say, well, okay, can we add the part of, yes, we could, but keep it simple. If not, we'll be like a monster.
I kind of have two questions. One is that I don't quite see how the weather falls into this model, or the climate. You said you had a 10-year scenario?
No, in this one, no. In the drought, we put the 10-year data about the climate. I think in this one, we had scenarios for varying prices, varying international prices in soybean and cattle. But I believe that in this model, the climate has nothing to do.
So then my second question was, if you had a good so you said you used a 10-year scenario.
Yeah, in the drought project, we used it.
Right. So, I mean, another approach which would get into some of the variability in climate was to just choose from the 10 years rather than having the sequence.
Yeah, we could do that.
And then you would get some of the uncertainty.
Yeah. Yeah.
Well, you still have to use a sequence because
Yeah, but in other words, if you run a model on a repeated sequence, it will idealize to that sequence. So it might take have artificial skill. It precisely adapts to that sequence. That you wouldn't see if you started picking the gear.
Yeah, well, actually, we didn't calibrate the model in a way that it would behave better with that climate data. But anyway, you clearly see the pattern, how in the output, you see the pattern of using the same climatic data from time to time. And actually, that data, we chose it because it had two drops. So actually, the first thing we did was to try to look into the past and see, well, our model with this data actually mimics more or less what happened. Well, and it did, fortunately. But of course, for the future, it's another story. we could perfectly have chosen the decision you suggest to randomly take one climatic data.
The information in here, or these kinds of things, there's an information gathering exercise or communications exercise. I guess some of the time people who are involved in agriculture and not just setting up model runs, what are the relationships and types of data sets that you're working with, and how much are you trying to get experts to give you good parameters through playing some of the spreadsheets and games, going to the, your partner research organizations.
Yeah, well, actually, we try to model and simulate things that some of our guys in our team are really familiar with or are actually experts on. Okay, so some of the data we are actually ourselves, which is questionable, by the way. Other data we gather it, as I said, with the sessions with the farmer. Other data of course, in papers, tables, and all that. But what actually happened to us a couple of times is that in this kind of multi-user system simulation, one of the good things is that you don't have to simulate your system under any equilibrium. You don't have to. And one of the good things is to shake it up and see what happens in a condition that is not an equilibrium. And in general, if you see some papers, you have like the graph of the relationship between how much the cow eats and its pregnancy rate. But that graph would go from A to B. But since these models are built in a bottom-up manner, I need it from 0 up to much more than the small piece of that the actual the paper that the guy gave us. So in many cases, we have to extrapolate, but it's not that easy to extrapolate because, for example, the graph growth. If you extrapolate it, you can get the graph over 2 meters, which is the graph dies by itself. Okay. So we have to shape up a little bit some curves, and those curves are actually data for us. Okay. So I don't know if I answered your question.
I have also. So you could have there like a crop model, isn't it? Like the things that we're running here at IRI. You already have a crop model there? It's like, or if I understand in this world, it's more like empirical. It's like, well, I know that I can't have like things 2 meters, height. So do you already have a crop model there? Because I understand the whole thing and the interaction. And this is, this is awesome. But do you already have a crop model there?
What do you mean?
Like how dynamic of the soybean or something like that?
Well, we did it, not for the soybean, but we did it for the grass growth in our drought. We actually mimic the actual growth of the grass on the basal soils with the climatic data we have and under the circumstances, under real circumstances. Not the same the graph space if you don't have animals than if you have animals like stepping over and all that. So actually, and I think it's reminded, but I didn't finish our 3-phase model. Our first phase of the model was to mimic only the grass growth, and that was actually what I guess you would say a crop model, because it actually mimics how the real grass behaves, at least in this region. Then we put the cows over that grass, and we had a big time in order to model all the animal grass interaction, which is quite complex. I realized that it was pretty complex because also you have competition over the different animals. Okay, so you have to see the available stock of grass and then see how many animals you have on that plot. And so you divide it by them, but that's okay. But you have a bigger animal that can like but the other one, well, other problems. And the first version, the third version of the model includes the users. So actual decisions are made over that. So we did like incrementally in those three things.
Yeah, and that's perfect because my other question is about that. Like your decision rules are static, they are constant, or your agents are capable of learning. Okay.
This is an example of decision rule. Again, this is not for the drought. This is for the soybean cattle dynamics. This is fixed. Okay, this is a decision tree that it is fixed. The thing is that on each time step, the computer will go for the branch that it corresponds. Okay, but it is fixed. You could make it learn. It's really, really hard to do that. Okay, we don't have any serious experiment with actual learning. You could do it. In our opinion, it's a very tough thing to do. Okay. And this is a UML activity diagram, and it shows you from the beginning of our time step to the end of the time step all the decisions that can be made by, I believe this one was the family producer, not the investment one, family producer. So he starts like using money to eat and to clothe himself and his family for all the year. Then we calculate how much money he has in the pocket. If he has too little money, he can start by building up for rent his investment fund manager. He can even start selling stocks to other family farmers, and eventually he can go bankruptcy and he exits the system. But only that instance of that type of farmer will exit the system. All the other instances, or the other objects will actually go.
What are the kinds of like examples, the kinds of insights you might be getting out of this effort? So what are the kinds of answers that you might communicate as a result of publishing a paper or as a result of modeling the policymaker? What are the kinds of things that that you try and say, this is what we've learned, or this is what we could learn?
Well, okay, where do I start?
Just an example.
Yeah, well, first of all, the policy making in this is an issue. Even it's very hard to see actual policy makers using this kind of multi-agent tools. Very hard to see examples, real-life examples of those. And that concerns.
So it's just like, here's the kind of question we're wondering about. Here's the kind of thing we've learned more about.
For example,
some examples.
For example, in the drought project, okay, the question was, which one of these strategies is better than the other? And our answer was neither, or both, or it's not that simple. Exactly, because we would run over and over again with different initial parameters, with different evolution of the parameters, with different scenarios, and of course, in some one would go bankrupt, and in the other one, but it was not any clear answer that, well, this strategy is clearly superior to the other.
What would be an example of a strategy, or the comparison, the difference between strategies?
Well, in our case, in this drought project, was this proactive versus reactive. The proactive one first looks at the grass height and starts to supplement when he is entering winter and the grass is not high enough. And the other one will start to supplement, the reactive one, only when the cattle start to die, because their mindsets are different. One guy wants to see less cattle but fatter, and the other one wants to see a lot of cattle in his country.
So when you say it depends, were there things that it seemed to depend on, or
no? It depends on the actual reality.
Yeah.
In our case, we discovered these two strategies. Okay. In another case, you should have discovered the strategies that apply for that reality. Okay. But the policy decision over this is actually.
Yeah, I know you mentioned you wanted to make things simple in a way. But for instance, the climate effect is mostly steep in grass. That's how you see the climate.
Yes.
So it has something to do, for instance, with incidence of
Not in our model. No. Again, we could have added that. We didn't want to.
I guess so climate is long-term. The long-term thing in this, I mean, clearly the individual farmer has the land. That's their capital investment, and they could go bankrupt and lose it. Do they have other capital investments? I mean, the thinking behind my question is most long-term droughts that have been true disasters are mostly a capital disaster. The farmer loses their capital goods and they can't farm anymore. So what capital goods are there for the individual farmers besides the land in this model?
Or have the land and the animals.
The land and the animals. So that's it. So that's the sort of the long-term risk.
Yes. Yes. But also, for example, for us, it was very important to see how you could recover from a drought if you end up the drought with 10% of your animals. How much time would it take you to recover that?
Is there also debt in this? Or no debt?
Well, we put it like a debt limit. Because if we put it like you cannot have debt, it was pretty tough. Everyone has to go bankrupt. Because in a drought, I mean, you have to go elsewhere and buy supplement, which is really expensive. And in many cases, you have to ask for a loan or debt or something. So we had like it was parameterized. We had like for example, $20,000 debt. What's your maximum? And only when you reach your maximum debt, you will go bankrupt. And of course, you year per year, you start to repay as long as you can. But when you reach the minus 20,000, you're done. Yeah, I mean, again, we could have made it more complex. What we decided to make it.
So they only depend on droughts, or they have also capabilities to use filings, for example. In Uruguay, you have your planting corn, you have your corn box that can be.
Yeah, well, the supplement.
Filing.
Yeah, the supplement that I talked is that you buy the big bags of.
The corn stuff that you can.
No, we only. Yeah, I guess that we model it as like you have bags of food and we don't care how you got that bag of food, but you have to pay for those bags of food.
I have to go over. That's what I think for us. You're getting a lot of questions that are very targeted. I would like one of the almost obsessions of the IRI is to understand how climate affects, in this case, production systems, and how a farmer, in this case, with his or her decisions, can affect that interaction of climate and production. Now, one of the problems that we have is that when we try to describe what a farmer could do and what government would support what a farmer is doing and what, an insurance program, what is the role in that, is that very often it's hard to quantify things. Very often it's hard to simulate, to have a model. So when I see your work, I think that the great value of this is that instead of talking in abstract, there are people that are more risk averse. There are people that are, the model may not be perfect. It may be a very simple caricature of the way that livestock farmers work. But you have two models of farmers that represent pretty well what Uruguayans livestock farmers do. So then you start asking questions. Okay, you use this as a static climate. What happens? Then you use with a real 10 years climate. What happens? Then you do what Ben is saying. You start resampling randomly. And for example, you may find that if you have 2 droughts in a row, the whole situation explodes. But what I think that this type of tool, this approach, is so valuable for us, is that it would help us to link with the social decision-making aspect of the process that we have been very frustrated for many years.
Yeah, actually,
we speak different languages, we have different tools, you know. Usually social scientists work at a very small scale and come here with a huge resolution.
Yeah.
So what I would like to think together is how can we start linking these two? The great thing of this is that this is an approach that allows you to start quantifying the impact.
Yes, and especially these kind of models let you put the social subsystems inside the model, not as an input. I mean, in the Excel spreadsheet, it is an input, but in the actual Cormas model, it's not an input. You are actually modeling these characteristic behaviors or rationales of the producer. And of course, I had many questionings from the social scientists saying, well, nobody will behave like that. Of course not. But what do we do? Okay, we don't model the producer. That's the solution. The solution is the more homo economicus, that they are all average people that only look to maximize their profit, and that's like the only activity they do, maximize profit. That's it, and they are all the same. Here you have heterogeneity in an individual base, if you want. So, of course, it's not perfect, and since you are putting people into the model, so to speak, you will have to do huge simplification. But what alternative do you have if you want to play around also with the farmers inside the model?
So I think that is the great right of this. You start playing with sensitivity. You know, for example, if you make the climate a variable, the decision-making a variable, then you can start asking questions like Dan was saying. Okay, now I understand this interaction of decision-making, climate, and production systems. So what is the role of an insurance program? You know, and how the insurance program will be more or less successful depending on what mental model the producer is using.
The effect on taxes over the issue, for example. If you tax the production, what happens?
I think that's a thing that I would really like for us. I'd like to start thinking of how do we connect to this. And then it's a learning process. You know, okay, these two farmers are not enough to represent the Uruguayan livestock. We need a third one that is whatever.
Well, for example, one of the farmers' actual feedback was, well, we are agree with these two, but it would be great to have a third option like in the middle. We couldn't put it in because we didn't have enough time, but it was a feedback that they gave us. And also, we had a couple of projects with the University of Brasilia in Brazil, and they have a couple of social scientists working on these multi-system models. And they already know that you cannot model everything and be super specific and people so different, blah, blah, blah. So they are like already, so to speak, educated or introduced in the thing, and they also, as social scientists, help to improve this model. In the social part, we are pretty weak now. Okay.
Well, I was going to more into what you said. That I used two similar stuff in the past, and the main goal is not to make forecasts, but to do sensitivity analysis.
Yes.
You have a system that has many different inputs, many different parameters, and many different outputs. And you change a little bit of each of those. You run patterns of simulation, and you say, and this outcome is sensitive to not to the rainfall, but to the international price. And that's what you got from that. You become this very flexible forecast.
Sure. And as you have to be very careful in not continue to adding complexity, you also have to be very careful in focusing. Right. The first thing, we have like a sort of step-by-step process in order how to engage on this kind of project, or at least from the software point of view. That's actually my master thesis. And like the first point is, well, what's the objective? What's the aim? What questions do you want to answer? Because then you would have to ask me, well, why don't we put the degradation of, what? We never talk about that. I mean, of course we could, but we shouldn't if we want to keep it simple and not build a white elephant that then we don't trust. If you don't trust these models, you're done.
Thank you very much.
No, please.
So you will
Thank you.
spend the whole day here?
Yes. No, without the letter. All day.
And also literally here.
I will be literally here.
For his office all day.
Yes. In prison, this forward. Good. Good. Yeah. And I will be more than glad to see you today or get in contact by mail or whatever. And again, thank you very much.
Thank you.
Te lo ganaste.
Súper interesante.
Bueno, llegamos.
Ya iba.
Está.
Muy buena.
Dale.
I definitely want to. I'm pretty
¿Cómo le gustó?
me encantó.
¿Me entendió?
Sí, sí, sí. Bueno, para mí es bien complicado, pero sí. Okay, right now I have a schedule to see, porque para mí la parte de clima es
Para muchas
más.
Sí. Y también es algo